All right, so I'm going to do questions number 3, 4, 5, 6 on the discussion worksheet number 3 upon request. So I know some of you did not finish this last week or the week before spring break. So I'm going to go over these step by step such that you have records of it for your studying and also to complete all the discussion worksheets. So I am going to start with number 3. So question number 3 states at 20 degrees Celsius, the carbon resistor in an electrical circuit connects to a 5-volt battery and has a resistance of 200 ohms. And the question is, what is the current in the circuit when the temperature of the carbon rises to 80 degrees Celsius? So in this question, we're going to mix Ohm's law with our equation of resistance as temperature increases. So I'll remind you that Ohm's law, again, will be change of potential is equal to the current times the resistance. So rearranging this equation and solving for I, we have I is equal to the change of potential divided by R. And in this case, we're going to change this value of R because the temperature will start at a reference temperature of 20 degrees Celsius, that gives you 200 ohms, to the resistance at 80 degrees Celsius. Okay. So once we find the resistance at 80 degrees Celsius, we can go and we can plug it here for R. All right, so let's remind ourselves the equation as a resistance changes with temperature. So I have R is equal to R naught, which will be our reference temperature. And then inside the parentheses, we have 1 plus alpha T minus T naught. So plugging this into my equation for I. So here, what I'm going to do is instead of writing R in this box, I'm going to write this whole component here to the right hand side. Okay. So this gives me that I is equal to my change of potential and then divided by, I have R naught 1 plus alpha T minus T naught. Okay, so I'll remind you that here my T naught is 20 degrees Celsius, T will be 80 degrees Celsius, alpha is the value of carbon that I have given it on top, and then R naught is our 200 here, R naught. Okay, so I'm going to plug these values into the calculator all in one go, and I will get a current of 2.6 times 10 to the negative 2 amps. And you are done with that question. That is all there is. Now, question number 4 will be slightly different because we're going to first solve for our R naught, our reference resistance, and then we're going to use that reference resistance to solve for a temperature. So I'm going to go to question number 4. So question number 4 has a platinum resistance thermometer that has a resistance of 200 ohms when it is placed in an ice bath of 0 degrees Celsius. Then it is immersed and the resistance goes up to 253.8 ohms. Okay. And it is immersed in a crucible of melting potassium. So the question is, what is the melting point of this potassium? Okay. What is the temperature such that I have this resistance that rises from 200 to 253.8 degree ohms. Apologize. All right, so I'm gonna write the equation to solve for R naught. So here, just like before, I can say that R naught is equal to R divided by 1 plus alpha t minus t naught. Okay. So I rearrange this equation for r naught. Alright, so I'm going to simply plug in the values here. So I have my R is 200 ohms divided by 1 plus 3.92 times 10 to negative 3 degrees Celsius, negative 1, and then we go from 0 degrees Celsius minus 20 degrees Celsius. And it fits here. So we have a R naught when we plug all the information of 217 ohms. Okay. Alright, so with this R naught, then we can go back and solve for the temperature. Again, try to do this at your own pace. But what we're going to do is we're going to solve for T naught. So I'll remind you here that we have R, which is the resistance, is equal to R naught. And you have 1 plus alpha T minus T naught. So here we're going to solve for this temperature because we have a reference temperature. This reference temperature is the 20 degrees, and then the equivalent reference resistance here is the 217. We are given the value of alpha, and we have our R, okay, because this value of R is 253.8 ohms. So the only variable that we're missing is this, for this R naught is T. Okay, so we have R naught, R, alpha, and T. So when you rearrange for the temperature, you will get that the temperature is equal to T naught plus R, oh, that's an R, R over R naught minus 1 all over alpha. And plugging the values in here, so again we have T naught and then R naught, you will get a temperature to be equal to 63.3 degrees Celsius. Okay. So try to rearrange this equation. You're going to solve for the temperature, and when you have the temperature, just plug in all the values, and then you will be done with this question number 4. Alright, so I'm going to do now question number 5. Question number 5 is a straight plug and chug. This is similar to what we did in lecture. I just want to make sure that some of the components that we do in class are known. But it is to use the power equation and go from using equation with power in terms of potential differences and currents, or potential differences and resistance, and back and forth. So here we have two light bulbs. We have light bulb A and light bulb B. Light bulb A has 25 watts at 120 volts, and light bulb B has 100 watts at 120 volts. And we're going to find a series of characteristics of these two light bulbs. So for part A, we want to find the resistance of each light bulb, and then part B will be what time interval does 1 coulomb pass into light bulb A. So let's do the resistance of both light bulbs. So for light bulb A, what I'm going to do is I'm going to rearrange this green equation between power, potential difference, and R, which is our resistance, and solve for R. So I have the resistance of light bulb A, which is equal to the change of potential quantity squared divided by P sub A, the power of light bulb A. So I'm going to plug in the numbers. This is just simply plug in the numbers. We have 120 volts quantity squared divided by 25 watts. And we have 576 ohms. To find the resistance of light bulb B, we use the same equation. The change of potential quantity squared over P sub B, the power of light bulb B, wattage, which is equal to 120 volts divided by 100 watts. Let me square the numerator before I forget. And this will be 144 ohms. Okay. Again, try to do these by yourself. Don't just copy me. Try and follow up. Okay, so we have the resistance of both light bulbs. And then we're going to find the time interval. So what we're going to do here in this space, hopefully it fits, let me use yellow, is I'm going to remind us that I can find the current of light bulb A to be P over delta V. And then we use another state, which is the charge Q is equal to the current of light bulb A, my bad again, times delta T. Okay? Charge would be the current times the passive time. So what I'm going to do is I'm going to plug this current of light bulb A into this equation. So I have P over delta V multiplied by delta T. And here, what we ultimately want to solve is for this delta T. Alright, so let me solve for this delta T. Let me put a squiggly line. So I have delta T is equal to Q, which is this Q here, times delta V, okay, when I cross multiply, divided by P. So I'm going to put in the values. So I have 1.00 coulombs. And then I have 120. Okay. So remember that the change of potential, the volts, can be written the units as joules per coulomb divided by 25.0 watts. Okay. Remember, the watts is joules per second. So that's how the units cancel. So then I have my delta T to be 4.80 seconds. Okay. Before I move to the other question, remember the watts. I'll say this again. Watts can be written as joules per second. Joules per coulomb. And joules per coulomb cancels, and then joules, and then 1/second goes to numerator, so your unit is seconds. Alright, part C asks about a theoretical component. So the question is the charge different upon its exit versus its entry into a light bulb? And the charge emerging is the same charge entering. Okay. So charge out is the same as charge in the light bulb. However, this charge has given 120 volts of potential as it goes through. Okay, so the charge is the same, but the potential has been, I should say here, parenthetically, given as it passes through the light bulb. Alright, so part D is in what time interval does 1 joule pass into the light bulb? So here we have, and light bulb A, by the way. In what time does 1.00 joules? Go put in red so I can use it. Alright, so here I remind us how we can also solve for power. So remember that power, which is 25 watts, can be written as joules per second. So if I rearrange the units, so again, using this unit, we wrote that power, which we have in watts, is equal to joules per second. So we can do that. Delta T is equal to the wattage P. Here we have 1.00 joules over 25.0. That's a point. Joules per second. So this is equal to 4.00 times 10 to the negative 2 seconds. All right. Almost there. This question, the next question, is actually very similar to question number 6. It's mostly the same question, which is finding the cost of running a light bulb continuously. So in this case, we're going to find a light bulb that runs continuously for 30 days, and we have a cost per kilowatt hour. So when you write the cost per kilowatt hour here, this question says the cost per kilowatt hour is 0.110 dollars per kilowatt hour. So to find the cost, we have the cost is equal to the energy used multiplied by the rate that you have. So we have, write this as P sub A times delta T times the rate that we have. Okay. So energy used times the rate. So let's put this all in one line. So I have 25 times 10 to the negative 3 kilowatts, and I'm going to use this for 30 days. Now, of course, we are giving a amount of time in days, and the way that we measure this is in kilowatt hours. So we're going to go from days to hours. So then I can go from days and say that one day has 24 hours. Okay, so the days and the days cancel, and I will multiply this by the rate, and the rate is 0.110 kilowatt hour. All right, when you plug this into your calculator, you have $1.98. So to run light bulb A continuously for 30 days will cost you $1.998. Right, and the last one is question number 6. Again, I'm going through these quite fast. These are older discussion problems, and you can stop the video and try them yourself. Please try all of them. So question number 6 is a car owner forgets to turn off the headlights of the car while it's parked in the garage. If 12 volt battery is rated to be 90 amp hour, each headlight requires 36 watts of power. How long will it take the battery to completely discharge? Okay, so in this case, how long will it take the battery is solving for time. So this is actually quite a fast problem. I'm going to make an assumption, which is quite obvious sometimes, is that I'm going to do a beautiful drawing here. I'm going to assume this is the front of a car, and this car will have 2 light bulbs. Okay, look at beautiful car. These will be the wheels. Alright, so there's 2 light bulbs, and then each light bulb will require 36 watts of power. Okay, and they're going to be identical. So the power, my assumption is that I have 36.0 watts plus 36.0 watts of 2 light bulbs, and this is 72.0 watts. Okay, 2 light bulbs in the car. So to find the power, what I'm going to do is I'm going to first solve for the current, and then I'm going to use the current to find the change of time, or the time to discharge. So you're going to have I is equal to P over delta V. Okay, this is the equation for power. In class, we solved it as P is equal to I delta V. Okay, that's how I presented it in class. So putting in the values that we have here, I have 72.0 watts. Okay, this is the power we just assumed here on the right hand side, divided by 12.0 volts, not 120, 12, I made a mistake. So here, if you plug this in the calculator, you get a very nice even 6.00 amps. So using this, I am going to remind us that we can solve for the charge to be equal to current delta T, and then I'm going to solve for this delta T. Okay, we did this in the previous example. So rearranging the equation, I have delta T is equal to Q divided by I. Okay. So this will give me a 90.0 amp hour divided by 6.00 amps. Amps will cancel. So we have delta T to be 15 hours. Okay, so you will need to wait 15 hours for the battery to completely discharge 2 light bulbs, each light bulb to be 36 watts. Okay, so these are questions number 3, 4, 5, and 6 in the discussion worksheet that you were missing, discussion worksheet 3.